Welcome back to the Deep Dive. Today we are cracking open a hidden assumption, one that underlies, well, nearly all of statistics and probability modeling. You, our listener, you use probability distributions every day, whether you realize it or not. These are, normalized measures where the total weight is always 1.
Right.
But when we take a real-world system, say a population of cells, and we force that total mass to equal 1, are we throwing away the most critical piece of information about how that system is actually going to evolve?
That is the ultimate puzzle. I mean, we normalize because it's convenient, right?
Of course.
It allows us to compare apples to oranges, whether we're tracking 100 people or 10 billion. But our mission today is to find the mathematical firewall, the necessary and sufficient condition that guarantees we can have autonomous, self-contained probability dynamics on that normalized space. When can the shape of the distribution evolve completely independently of its total size?
And the sources provide this beautiful, unifying way to look at it. A conceptual reinterpretation that really reframes probability itself. We're going to stop thinking of probability distributions as static charts and start viewing them as waves.
Precisely. Imagine your probability distribution, the likelihood of finding a value here versus there, as a wave propagating through a medium. The standard probability simplex, where everything sums to 1, is just a choice of normalization.
A choice.
We're enforcing a constant wave amplitude. So the entire deep dive hinges on figuring out when does enforcing that constant amplitude preserve the original true physics of the wave.
Okay, let's unpack this. We have to start with the fundamental space where everything lives before we apply any kind of normalization rule.
We begin with the base object, the positive measure cone, what the sources call 1 $1 plus x doll. This is the space of all finite non-zero positive measures. Woo.
Got it.
Crucially, every measure lives here, regardless of its total mass. It tracks the distribution and the magnitude.
So if I'm modeling, say, the distribution of wealth in a country, the measure mu in this cone captures both the Gini coefficient, that's the shape of the distribution,
Right.
and the total GDP, the overall magnitude.
Exactly. It holds all the information.
Right.
Now, standard probability lives on what's called the probability simplex, px.
Okay.
This is the space where the total measure mu of x equals 1. Geometrically, px is a global section of that cone.
A global section. So I'm picturing the cone pointing upwards from the origin, just slicing across it horizontally at the height where the total mass is exactly 1.
That's the visualization. Normalization is the map, let's call it pi, that projects any measure mu onto its normalized shape, which is p, px, x, x, m. This map takes the entire cone and just crushes it down onto that single slice, px, throwing away all information about the original height, the total magnitude.
To understand the physics of this, the sources give us this elegant logarithmic decomposition. They read it as lambda wo. This is the key to our whole wave analogy, isn't it?
This is where we separate the signal. We split the measure into 2 information channels, and it's kind of analogous to old radio technology.
AM and FM.
Exactly. The first is rho, which is the log of the total mass. This is the log scale, or the AM channel, amplitude modulation. It tracks the total mass, the sheer loudness or intensity of the wave.
Okay.
The second is P, which is the measure divided by its total mass. This is the shape, or the FM channel, frequency modulation. This tracks the normalized pattern, the tune or the phase of the wave.
So we're saying that every probability distribution is basically a radio wave carrying 2 messages.
Yeah.
How loud it is, its AM signal, and what pattern it has, its FM signal.
Right.
And standard probability theory just assumes we can turn off the AM channel and the FM channel will still function perfectly.
That is the challenge we face. When we discard the AM channel rho and try to define the dynamics solely on the FM channel, bra-P, we are assuming that the shape's future evolution doesn't depend on the wave's loudness.
Which brings us to the algebraic criterion in section 2, the normalization obstruction. So if we have a measure evolving in time, when is its normalized shape, P of t, truly autonomous?
This is the algebraic core of the whole thing. Autonomous probability dynamics exist if and only if the system's generator, let's call it L, commutes with the dilation operator D.
Okay, $1 D equals in the form.
That's the one. $1 D equals dollars.
Okay, let's slow down on the algebra because this is the central takeaway. What exactly is this dilation operator D doing in plain language?
Right, so the generator L describes how the measure evolves in time. The dilation operator D is Well, it's the generator of scaling. It tells you how things change when you just multiply the entire measure by a constant factor.
I see.
In our logarithmic coordinates, d is simply the derivative with respect to the log mass with respect to rho.
Okay, so the condition $1, d equals dollar with L, means that applying the evolution rule L and then scaling with d gives the exact same result as scaling first and then evolving. The order doesn't matter.
The order doesn't matter. Scaling and time evolution are interchangeable. Algebraically, this just means the evolution operator L must be homogeneous of degree 1.
Right.
If I start with a measure mu, and I scale it by a factor of 10, the resulting evolution L of mu must also be scaled by a factor of 10.
That makes a lot of sense. It means the physics of the system is the same whether you have large sample or small one. So if the system isn't homogeneous, if that commutator isn't 0, that's the obstruction. What's the real-world consequence?
The dynamics are not scale invariant. Normalization breaks the connection. When you look at the shape P, you find that its speed and direction of evolution depend explicitly on the total mass.
Ah.
The FM channel is coupled to the AM channel. The probability wave needs to know its own loudness to know where it's going next.
And here's where it gets really interesting. Because that single algebraic condition, that commutator being 0, it provides this profound duality, linking physics and geometry. Let's unpack this twin interpretation.
Let's take the wave interpretation first, because I think it's the most intuitive. The condition Waller-Dallard d equals wonder is the requirement for the system to be non-dispersive.
Non-dispersive, like a light wave traveling through a vacuum where all the frequencies travel at the same speed.
Precisely. If L is homogeneous, the total amplitude, let's call it R, it just cancels out in the equation that governs the shape's evolution.
Okay.
The phase velocity is independent of the wave amplitude. Whether the probability wave is intense, a strong signal, or weak, a faint one, it evolves its pattern at the same relative rate.
So if the commutator isn't 0, the system is dispersive. This means the phase velocity depends on the amplitude. My quiet probability wave travels slower or faster than my loud one.
Exactly.
It's like the total magnitude is acting like a variable refractive index.
You got it. Now for the geometric side, when Wall dollars, d equals NYS dollars, the structure of that measure cone, weather dollars plus economics, is mathematically flat. You can picture perfectly straight lines radiating out from the origin.
And that flatness means the evolution of the shape, PP, stays completely parallel to the normalized base, no matter how high up the cone, how large the mass it is.
Exactly. The flow does not bend. But if $11, d nec dollars dollar, the system is non-homogeneous, and that cone becomes geometrically curved. That bending, or curvature, is what links the normalized shape back to the total mass. Curvature is the obstruction.
This is a powerful synthesis.
Here.
So whether you look at it geometrically as curvature or physically as dispersion, the unified conclusion is that the obstruction arises when the system exhibits self-interaction through total mass.
Yes.
The probability medium changes its own rules based on its intensity.
The system feeds back on itself. Geometrically, the trajectory bends because of its altitude in the cone. Wave-theoretically, the probability wave is surfing on its own intensity, changing the propagation rules as it grows or shrinks.
This sounds theoretical, but Section 4 provides the critical proof by fire. It shows that this criterion perfectly separates the linear standard models from the messy, complex ones. It's like a spectral filter for stochastic dynamics.
It's remarkably clean. Let's look at the non-dispersive systems first, the ones that obey $1 d equal d.
The gold standard. Bayesian updating.
Bayesian updating is non-dispersive. Why? Because the process of updating your beliefs is a linear transformation. When you multiply a prior distribution by a likelihood function to get a posterior, it's a linear map.
Okay.
The likelihood acts uniformly. Whether your prior belief is intensely held, a large amplitude, or weak, the relative rate of change is identical. Normalization is valid.
Another system that seems complicated but stays linear is the Feynman-Kac semigroup. These are used all over finance and physics.
Right, and while the total mass in a Feynman-Kac system often grows exponentially, the underlying evolution operator, fate team, is still linear.
So it scales properly.
It scales properly. The growth is uniform across the entire measure. It just factors out globally. We call this amplitude amplification without dispersion. The phase evolution remains independent of the total growth, so normalization holds.
The key is that the killing or attenuation pattern depends only on where you are, on your position x, not on how much mass is currently there.
Exactly. The medium is passive. It doesn't react to the wave's intensity.
Okay, now for the fun part. The dispersive systems, where the well dollar, d nec Wohl's dollar, this is where the coupling happens, and the system is forced out of that classical framework. Let's start with the most obvious one. population-dependent branching processes.
In these systems, the birth and death rates, lambda, depend explicitly on the total population size, n. This is the paradigm of self-interaction.
Right, so if the birth rate depends on how crowded the environment is, a high population means fewer resources, which slows growth, then doubling the initial population doesn't just double the outcome. It fundamentally changes the rate of relative change.
Exactly. The take to most sins emphatically not to most.
Yeah.
Dense populations evolve qualitatively differently than sparse ones.
So the theorem instantly confirms the intuition of every population biologist. You must track the total population size separately.
You have to. The AM channel, the total mass, is required to predict the future of the FM channel, the shape.
And we can see this mechanism perfectly in the source's analysis of logistic growth. The evolution speed for the shape, P key, depends explicitly on E to the rho, which is the total mass. Tell us what that coupling looks like.
This is pure dispersion in action. The shape evolution speed is determined by the total mass. When the mass is low, the system behaves linearly. It's basically non-dispersive.
Okay.
But as the mass approaches the carrying capacity, that phase velocity slows dramatically. The probability wave is effectively slowing down because it is too loud.
The loudness is changing the medium it travels through.
Precisely. The system is changing its own refractive index based on its intensity. This is why if you try to model this with a standard normalized probability distribution, you will fail to capture the long-term behavior.
And the general case, mass-dependent killing. If the absorption rate kappa depends on the total mass,
then normalization fails. Intense probability waves experience different damping than weak ones. The amplitude is determining the phase decay.
So the profound realization here is that classical probability theory, which relies on normalization, corresponds exactly to the non-dispersive scale-invariant regime of stochastic dynamics.
That's the takeaway.
So what does this all mean for us, the model builders? If normalization fails because the medium is discursive, how do we fix it and maintain our predictive power?
Well, you must put the discarded information back. Normalization is a form of AM clipping. You're cutting off the amplitude information.
Right.
And if the AM and FM channels are coupled, clipping corrupts the signal. To restore what's called Markovian closure, you have to move to the enriched state space.
The enriched state.
Yeah.
We're moving from that simple slice P of X back to a richer space.
The joint state E tracks three things: the normalized distribution P, the total mass M, and the distribution of any other internal invariance you need.
Okay.
You are guaranteed that this joint enriched state will evolve autonomously, even if the shape P alone cannot. You are essentially tracking the complete wave, amplitude, and phase together.
And the elegance of this new framework is that it yields a mathematical shortcut, what the sources call a projective calculus for probability. It lets us see concepts we thought were abstract statistical rules as concrete geometry.
It places probability squarely in the world of projective geometry. For example, Bayesian updating is revealed to be a projective collineation.
A collineation.
Think of it as a geometrically stable transformation. When you update your beliefs, the underlying structure of those beliefs remains fixed and predictable. It's an incredibly rigid, fixed process.
And what about the concept of independence? That seems intuitive, but it has a beautiful geometric structure in this view, too.
Independence is constrained. Two random variables are independent if and only if their joint distribution lies on a specific geometric structure called the image of the Segre embedding.
So independent distributions don't just fill up the whole space.
Not at all. They form a proper, specific subvariety within it. It's a very special and very small set of distributions.
That's a stunning insight. It turns an abstract statistical property independence into a physical, observable shape within the probability space. You can literally geometrically test for it.
The conclusion is powerful and it's final. Classical probability works perfectly when the medium is linear or non-dispersive and the geometry is flat. Nonlinear dynamics, which introduce scale dependence, are equivalent to introducing curvature and coupling.
So if you are building any dynamic model, the very first step should be to check if your system's generator, L, is homogeneous. If it is, you can work safely in that clean, normalized space. But if it is not, you instantly know that you have to track the total measure or your model will fail to capture the true dispersive dynamics.
The obstruction, $, next dollars, it's a structural warning signal. It tells you the exact boundary where self-interaction requires you to move beyond the classical normalized framework and start tracking the wave's amplitude.
The sources suggest that by framing probability distributions as waves, we are forced to look at probability theory not as the universal language of chance, but is the description of a highly structured, linear, non-dispersive regime.
Normalization is a mathematically necessary projection for that specific linear class of problems. It's not an inherent law for all evolving stochastic systems.
Which leads us to the final provocative thought for you to mull over. If probability distributions are indeed waves whose dynamics are governed by dispersion relations, what implications does this wave analogy hold for predicting rare events or understanding phase transitions in complex stochastic systems? Similar to how wave focusing leads to dramatic outcomes like rogue waves in highly nonlinear media.